Hello data scientists, welcome to Skillgate. In this course, we will cover a business relevant face recognition project end to end. Before we get started, a little bit about us. Skillgate envisions to provide you hands-on experience of industry-ready projects having real-life complexity. Every project we bring to you solves a real business problem end to end through a data science approach. Along the way, we will share DIY kits with you, having a dummy business case, problem dataset, Python code, and additional business analysis tools for you to solve these problems yourself. If you are a student, you may create academic projects through our courses, or if you are a working professional, you may contextualize our courses further to solve your business problems. Needless to say, you may always reach out to us for any help you may need to achieve your objectives by commenting below or through our contact details provided in the description part below. Alright, let's get started. This is Skillgate's problem solving framework. We will go step by step through this framework to understand, solutionize, and deliver on our project in hand. First thing first, let's understand a face recognition problem from a business standpoint. Every business facility or a corporate office has an access authorization process in place to authorize each and every individual demanding entry into its premise. This authorization process could be completely manual, wherein a security guard sits at the entry gate and allows individual he knows by face or authorizes them through their company ID cards. In the last few years, majority of businesses have now moved to an access card based or biometric based access authorization system, which has made this security check process quite easy. However, all three of these access authorization modalities have their downside. While security guard driven authorization process is susceptible to manual errors or bribes, access cards have a risk of misuse by unintended users, and biometrics involve human contact which carries a risk of infection and diseases. Thus, need of the hour is to have an access authorization process which is as personalized as a biometric, as accurate as an access card, and as robust as a security guard based screening while being completely contactless. Well, that's where face recognition based access authorization comes in. Only downside to this approach is that we need data to train a machine learning model, but that for sure is a small price to pay for a completely secure, seamless access authorization system that businesses would get in return. Face recognition machine learning models can accurately recognize individuals with minimal to no manual intervention. Needless to say, such a system is immensely scalable and is state of the art. Alright, now when we understand the business use case for a face recognition project, now it's time for us to understand our dummy client ABC Limited's business case. Our client ABC Limited intends to adopt face recognition based access authorization in a big way. To start off, they want us to do a small POC for their boardroom, which is accessible only to a few senior leaders. So the required face recognition model should recognize and grant access to all these senior leaders who are authorized to access this boardroom and also deny access to everybody else. Business has shared face pictures of these senior leaders that we would use for training our model. Let's deep dive into our data further. Alright, these are ABC Limited's four senior leaders that are authorized to access the boardroom. Yes, these are indeed Bollywood celebrities whose pictures are readily available on the open source. We use such celebrity pictures often in educational machine learning projects. In a real business scenario, you would indeed have the real photos of company employees. Anyway, we have decent number of face images for our four senior leaders. As you may observe, for Anupam Kher, we have somewhat less in comparison to others. And this would reflect in our model performance, which we would discuss in the last part of this video. All images given to us follow a standard naming convention, Example, all Amir Khan images have prefix Amir followed by a number. These file names would help us to generate labels for these images, which we would further discuss in the model building part of this video. Alright, this personally is my favorite part. Let's understand how we would go about solving our client's business case with a machine learning approach. With this next section on solutioning intuition. This is our solution architecture for face recognition based access authorization system. This entails a camera that clicks a picture for individual demanding access into the building. This image is handed over to the face recognition machine learning model that in turn classifies this individual as identified or unidentified and grants access accordingly. Here, our scope is this part outlined under this dotted red box. We shall assume camera and other hardware installation is already in place, and our part is to train this face recognition machine learning model and ensure appropriate model performance. As we now know that our machine learning model shall take image data as input, let's discuss image data and the challenges it offers. Not all data is created equal. Some of it is structured and the vast majority is unstructured. Just to give you a perspective, by year 2022, around 93% of world's data would be unstructured. Audio files, video files, emails, Twitter, Facebook posts, and image files are all unstructured data. Challenges with this unstructured data is that it requires significant feature extraction efforts to convert it to a representation that would be used for machine learning model building. Next up, we will discuss how exactly do we extract features from image data. For image data, there is a whole branch of feature engineering that deals with extraction of features from images. Here's a quick intuition on feature extraction from images. To start with, let's take a simple example. In this black and white image, clearly we may observe that it's a number 8. But the question is, how would a computer know that it's a number 8? The answer lies in how a computer stores this image data, which is basically a matrix. This particular image has a size of 22 by 16, meaning there are 22 pixels along the height and 16 pixels along the width. And in totality, there are 352 pixels. A computer stores a number between 0 and 255 for each of these 352 pixels, and this number is a measure of the respective pixel's brightness. As you may clearly see, brighter pixels have a value approaching 255 and darker ones have values approaching 0. With this understanding, a very simple way to represent features for this image could be to append all these rows horizontally and have a 1 by 352 matrix. That's about black and white images. Things would change slightly for a color image. Over here, the computer would store 3 pixel matrices, one each for blue, green, and red color intensities. Again, on a scale of 0 to 255, depending on brightness intensities. We may replicate the previously discussed approach for black and white image here as well. For that, we simply need to prepare a new pixel matrix carrying mean pixel values for corresponding pixels from the 3 matrices, which are called as channels. Further steps are the exact same as discussed previously. While this approach of feature extraction from images is simple, it is prone to a lot of problems. Consider we are comparing these two images. We have extracted features for these using our simple approach. As we may observe, this second image has a background while the first does not. Also, the color of the two dogs are very different. And not just that, even the expressions of the two dogs are different. All these factors are collectively called as noise. A good feature extraction approach would tend to minimize this noise. And clearly, our simple approach cannot do it, as it directly uses image pixel intensities. Not just that, our simple approach is computationally expensive as it retains so much unnecessary information that a good feature extraction approach may otherwise drop. Hence, we need a more systematic approach to extract features from images, an approach that retains only the crucial information while discarding the rest. For achieving this, we use HOG or Hog Feature Descriptor. Simply put, Hog computes pixel-wise gradients and orientations and plots them on a histogram, and hence the name histogram of oriented gradients. For this original image, this is the Hog representation. As you may observe, Hog has simplified representation of this image drastically, retaining only the most important information. This way, Hog is able to minimize overall noise here. In the coming slides, we would go step by step into building this Hog representation for this sample image. We would try to cover the in-depth intuition without going too much into technicalities. First step is image pre-processing, wherein we would standardize image size. When we are building a face recognition machine learning model, we are feeding tons of images for training our model. And it is very important for us to ensure all images are of equal size. In our case, we are resizing our images to 32 by 64. This means we are having 32 pixels along image width and 64 pixels along image height. Next up, we would divide our resized images into 4 by 4 cells for calculating gradients and orientations, which we would discuss next. Just to highlight here, it is recommended to resize the images to 64 by 128 and keep cell size as 8 by 8 or 16 by 16. But in our case, the input images themselves are very small. So we are using small resize and cell size values. Alright, this is the fun part. As we already know, Hog is histogram of oriented gradients. In this section, we would calculate the gradient and orientation, which we would then plot on a histogram in the next section. Here we have divided our image into 4 by 4 cells. As you may see, we have 8 such cells along width, denoted by this C8, and 16 cells along the height, denoted by C16. For this first cell, let's assume this is how the pixel value matrix is like. As you may observe, this is 4 by 4, the way we discussed previously. The first thing we have to calculate here is gradient in x and y directions that we call gx and gy. Gradient in x direction or gx is the difference of pixel values on the right of this highlighted pixel to the pixel value on the left. So this is 89 minus 78 equal to 11. Alright, this is our gx. Similarly, gradient in y direction or gy is the difference of pixel values above this highlighted pixel to the pixel value below. So this is 64 minus 56 equal to 8. This is our gy. Now to calculate the total gradient magnitude and orientation from these gx and gy gradient components, we would use Pythagoras theorem. Yes, the one we studied in school. So the total gradient magnitude is the root sum of squares of gx and gy, which is 13.6. Similarly, orientation is the inverse tangent of gy by gx, which is 36 degrees. Similarly, Hog algorithm would compute gradients and orientation for all these pixels of this selected 4 by 4 cell. For the image edge pixels, Hog uses a technique called padding. Please refer to the link in the description part of this video to know more on padding. Next up, let's try to plot these gradient and orientation values on a histogram. Gradient and orientation values for our highlighted pixel are 13.6 and 36 degrees respectively. We already know that this orientation value may vary between 0 to 180 degrees. For the histogram, HOG prepares bins of 20 degrees each. So there are 9 bins in total. Next up, Hog would start inserting gradient magnitude values as per the pixel orientation into these 9 bins. For our highlighted pixel, orientation is 36 degrees, which is closer to 40. So the major contribution of gradient magnitude would go to 40-degree bin and the minority would go to 20-degree bin. We use angle weights to do it. Simply put, 16 by 20 is the weight that is assigned to the 40-degree bin, which is the major chunk of gradient magnitude, and 4 by 20 is the weight assigned to the 20-degree bin, which is minor. Similarly, all other gradient values are added to this histogram based on their pixel orientations for the selected cell. Towards the end, we get a 1 by 9 feature matrix for this cell. Then, Hog would compute such 1 by 9 feature matrices for the remaining cells. Once done, next step is normalization. Localized gradients of image are sensitive to overall lighting. We can partly reduce this variation by normalizing the gradients. For this, we make groups of cells known as blocks. Here, we have grouped 4 cells into each block. Hence, we have a total of 7 blocks along the width and 15 blocks along the height when we shift this block one cell at a time like this. Alright, for a cell, Hogg previously prepared feature matrices of 1 by 9 each. Typically, a normalized matrix for a block would have cell features appended horizontally. So for a block, a normalized matrix would be 1 by 36. Now to get a normalized vector for this block, we need to compute this k, which is the root sum of squares of all 36 block features. Then we divide all features with this computed k to finally reach out to normalized vector for this highlighted first block. Similar way, Hog would compute normalized feature vectors for all 105 blocks by moving this block one cell at a time, both along the image width and height. Once done, Hog appends the 36 features from all 105 block normalized vectors horizontally, giving us a 1 by 3780 dimensional image descriptor. We could validate this number during the coding part. Well, this completes intuition on Hog feature descriptor. By the way, 3780 are a lot of features which would make our model building part computationally very expensive and might lead to overfitting as well. So we need to reduce these dimensions, for which we would use a popular dimensionality reduction technique called PCA. Principal component analysis, or PCA, is a popular dimensionality reduction technique. Not all features in our dataset are equally important. Some of these features may very well be dropped, making our model building process less computationally expensive while reducing chances of model overfitting. And PCA would do exactly this for us. It uses a mathematical approach to find an alternate representation of the given feature set, ensuring retention of highest possible variance and minimization of correlation among features. Let's understand these 2 points further with the help of an example. Firstly, let's discuss how PCA retains the highest possible variance. Over here, we have data of 6 houses capturing 3 features: value of the house, total area, and number of floors. Let's analyze this data from a PCA dimensionality reduction standpoint and understand which variables are more important than others. For this, we would need variances for these individual features. We have already done this computation. For your reference, this is the formula for variance. With this information, we can clearly observe that floor has a very small variance value. From an intuition standpoint, what this means is that I cannot distinguish one house from another using this feature. As you may see, floors are almost similar for all 6 houses and certainly do not help us much in distinguishes one house from another. Now if we plot number of floors with house value on this two-dimensional chart, We may observe very small variation along y-axis, which is floor, when x-axis, which is value, shows a lot of variation. Value, by the way, has a contrastingly high variance anyway. And at this point, it would make a lot of sense if we could reduce this two-dimensional chart to a single dimension. For that, we would project these red points to x-axis, which is value of the house. And voila, we have successfully dropped one variable. As you may observe, we still are able to retain almost the entire variance through these two variables that are contributing the majority of it. Next up, let's understand how PCA handles correlation. For these remaining two features, value and area, we may observe that value is roughly double the area. On a two-dimensional chart, the two features would show an approximate linear relationship like this. What if I told you that this chart could be reduced down to the same representation we discussed in the previous part on variance? See this. Isn't this great? Now this tilted x is what we call a principal component. Axis perpendicular to it is called an orthogonal component. Now, as there is more variability along principal component, we get a new feature by projecting these points to this principal component axis, which is exactly as we did in the first part. PCA is all about finding these principal components and picking the initial few of the components that explain most of the variance. This completes intuition on PCA dimensionality reduction. In the next part, we would discuss intuition on the support vector machine that we would use as our model classifier. Here's a quick intuition on support vector machine or SVM. SVM is a popular binary classification algorithm in the machine learning ecosystem. It is a supervised machine learning model as it requires labeled data for training. For classifications, SVM inserts a decision boundary called hyperplane between its binary classes in a way that maximizes the margin from the nearest elements of each class. Let's understand this further through an example. Here, we have these training data points already plotted on this chart. The blue circles belong to the first class and the red triangles belong to the second class. As is clear visually, the two classes are linearly separable in this example. So SVM's job here is to insert a hyperplane in between these two classes. Just to be clear, in this case our hyperplane would just look like a line on this two-dimensional chart. Out of all the lines that could be drawn between these two classes, SVM would choose the one that maximizes the margin from the nearest element of each class, as is the case here. Clearly, we may see with this darker line, which is our best hyperplane, SVM model is able to maximize the margin from these two nearest elements in comparison to a smaller margin for this second line. Let's go a little deeper into SVM to reinforce our understanding further. In this case, although the classes are clearly separated, we cannot draw a linear decision boundary like in the previous case. Basically, we need a non-linear decision boundary here. For achieving this, we would create a new dimension z and calculate the z component as per this formula, which is z equal to x square plus y square. You may observe this is the equation of a circle. With this formula, z components for all these points would be in the positive direction. Also, blue ones would be closer to the origin as their x and y components are smaller, and red ones would be farther from origin as their x and y components are relatively large. Here's a small animation for you to observe this in 3 dimensions. As you may observe here, both classes are now separated along z dimension, such that we are able to insert a hyperplane in between. Cool, right? Now all we need to do is to project coordinates of this highlighted circle back to two dimensions, and we get our decision boundary like this. With this, we may conclude by saying that SVM is a simple yet powerful machine learning model that can handle complex feature sets with ease. And this completes Intuition on SVM. This finishes our section on solutioning intuition as well. Next up, we would build our face recognition machine learning model applying Hog feature descriptor, PCA dimensionality reduction, and SVM classifier. So let's get coding. Before we get started on the coding part, there are certain prerequisites you would need to know. First, we would use Google Colab for Python coding, which is Google's free cloud-based platform. We have already done a small video on getting started with Colab. Refer to the description part below for the video link. Second, you would need to create a new folder with the name Face Recognition with SVM in your Colab notebook folder, just like this, and copy all these model related files here. Link to our free Skillkit DIY toolkit having all these model files is provided in the description part of this video. Over here, this folder 1.1 is having senior leaders photos that we would be using for model building. This 2.1 is our code file for building our face recognition model. Let's open it to get started. Alright, we are on Colab now. First thing first, let's connect Colab to our Google Drive. For this, click on this folder icon, then click on Drive, and then connect to Drive. Let's go section by section through this code now to understand what our code does. In this first section, we are setting the working directory to our newly created Google Drive folder. Let me run it. Next, we are importing all essential libraries and functions we would be using further in our code. Let's run that as well. In this third section, we are processing our image dataset to obtain Hog feature descriptors for each image and generate labels using the image file name. As we have already discussed during the Hog intuition part of this video, we are resizing our images to 32 by 64 pixels. Then we are computing Hog feature descriptor for all these images, keeping orientation as 9, cell size as 4 by 4, and blocks per cell as 2 by 2. We are then appending each normalized feature vector to this X, which we have initialized as empty over here. Similarly, for getting labels for these images, we are checking file name initials for Amir, Jaya, Ritik, and Anupam with these keywords and labeling them as 0, 1, 2, and 3 respectively. Then all these labels we are appending into this Y, which also we have initialized over here. Let's run this cell. It might take a few minutes for it to execute. Now, just for validation, we would print this FD that tells us the dimensions of normalized vectors. If you may recall, it should be 3780 and it indeed is 3780. We are also declaring full names of our labels 0, 1, 2 and 3 here as target names. Alright, now we have our images converted to numerical representation. In this next section, we are splitting this dataset into training and test in 80-20 ratio. As we have already discussed, 3780 dimensions are computationally expensive to handle. Thus, we are using PCA for dimensionality reduction. You would be surprised to know that we are able to reduce our original dimensions of 3780 to a mere 25 with PCA, while retaining majority of information. Let's run it. Then we are transforming our training and test dataset with our computed principal components. Also, we are storing these computed PCA coefficients back to Google Drive so that we can use them later in the prediction part. Next up, we are training our SVM model for image classification. We are using RBF kernel here, which basically tries to find a non-linear decision boundary in between the classes. For parameter tuning, we are using grid search methodology. This CLF.best estimator contains the tuned parameters for the optimal SVM model that gives best accuracy. Well, our face recognition machine learning model is now ready. We are saving this model file back to Google Drive for using it later during predictions. Alright, in this next section, we are evaluating performance for our trained model. Here, first up, we are predicting labels for the test set with this Vipred. As you can see, for the test set, our model is classifying images as 0, 1, 2, and 3. Now, let's obtain the performance summary with this classification report function. As you can see, our model has an accuracy score of 85%, which is quite good. Alright, from a model building standpoint, coding ends here. Next up, we would be using this face recognition model for access authorization on a new set of photos. As you may see, our PCA coefficients and SVM classifier model files have gotten created in our working directory. For access authorization dry run, we have kept few pictures in this new photos folder. This 2.2 predictor code file would help us to do this dry run. Alright, let's do it. Here also, we would first connect Google Drive to Colab. Let's do it. In this first section, we are setting the working directory. Next up, we are importing the same set of libraries as we did for model building. In this third section, we are loading the image file from the new photos Google Drive folder. We would uncomment one image at a time from these listed pictures to analyze our model classification accuracy. For now, I am keeping the first image of Amer as uncommented. Let's run this cell. You would also be able to see this loaded image as is the case here. Next up, we are computing hog descriptor for this image file. Alright, as you may observe, this also has 3780 dimensions. In the next section, we are reducing these 3780 dimensional dataset to 25 dimensions using the previously stored PCA coefficients file. Alright. Next up, we are calling our previously stored SVM classifier to obtain the class labels for this new image. As you may observe, we are keeping the probability threshold to 60%. What it means is that our model would only assign a class to this new image if it is at least 60% confident with this classification. Else, this image would be classified as unidentified, which intuitively speaking does make sense. Let's run this for Amir Khan's image that we have loaded. As you may see, our predictor is rightly classifying person in this image as Amir with 96% confidence, which is correct. Now let me run this entire predictor code for Ritik Roshan. Even now, our predictor is rightly classifying person in this image as Ritik with 97% confidence, which is again correct. Next up, let's see how our model classifies an unknown face. For this, let's run our predictor for Amitabh's image. You see that? Our model is rightly classifying the person in this image as unidentified. As this 31% confidence is below our configured threshold of 60%. However, as we have discussed during model building part, our model has 85% accuracy. Some misclassifications could also occur. To observe that, let's see how our model classifies this Anupam Kher's image. As you can see, this is a case of incorrect classifications, which is undesired. No model gives a perfect 100%. What we can do going forward for our client ABC Limited is to keep bettering the model accuracy score of 85% or implement a better machine learning approach like a neural network to better suit business needs. With this, our job as data scientist is more or less done, except for the last part, which is delivering this solution. For this, we need to prepare a client solution delivery presentation, something like this. Let me quickly run you through this presentation as well. Our deliverable for this assignment was a face recognition based authorization model for automating security for ABC Limited's boardroom. Our scope of work in this solution architecture was to build the machine learning model only. These were our assumptions. We resized image to 32 by 64, kept hog cell size of 4 by 4 and block size of 2 by 2, picked 25 PCA components and kept model matching confidence threshold to 60%. Then we trained our face recognition based authorization model to classify individuals seeking entry into boardroom premise as identified and unidentified using SVM classifier. As a deliverable, we have trained a face recognition based authorization model that has 85% accuracy. As we have used Google's free computational resources, there is minimal operational cost to business with our approach. As next steps, we would discuss with our client to kickstart this planned POC go live for boardroom. That would require infrastructure setup and manual system hand-holding from ABC Limited security team, along with technical hypercare from Skillgate. For phase 2, we would need to draft a full-scale launch strategy with ABC Limited on the scope and adjustments, refinements, upgrades from the boardroom POC. Alright, with this, we have completed our course on face recognition based authorization system. Please share your queries and feedback in the comment section below. If you want to see more such machine learning videos, do like, share and subscribe to our channel. See you in the next video. Till then, keep learning.